morning again. I would like to invite you to our next session, which will be the defeating sandbox evasion, how to increase successful emulation rate in your virtualized environment. And my pleasure is to invite to the stage Stanislav Skuratovich and Aliaksandr Chailytko, both from Checkpoint Software. Please.
Thank you. So, hello everyone. Thanks for attending our presentation. Our topic today is one of the hottest topics on the research scene at the moment. So I hope you will enjoy the talk. Quickly about who we are. My name is Aliaksandr, and I'm leading the team of highly talented reverse engineers. And here is one of them, Stanislav. Please welcome. And today we have a lot of things to cover, so let's go straight to the point. Okay, so we'll focus on bugs found in Cuckoo Sandbox, which may lead to the detection and evasion of it, and then we'll propose fixes for them. In addition, we will do the same for different virtualized environments, and finally we will present our sandbox detection tool, which contains most of the detections known till this date. And our tool can be easily configured through using the JSON configuration files and can be used for assessment of your internal virtualized systems. So now I'll transfer the presentation to Stanislav, and he will guide you through the first part of it.
Okay, thanks, Aliaksandr. Cuckoo Sandbox is a leading open source malware analysis system, and let's discuss bugs we have found in it. The first one, and probably one of our favorite ones, is technique called unbalanced stack. It may be applied to any type of user mode functions hooking. They use the similar hooking technique as Cuckoo Monitor does. Let's take a look what happens if function hook are not present. At first, we push function arguments on the stack. After that, we move stack pointer towards lower addresses on the space we need to store return address and function local variables. And after that, we store unbalanced stack canaries under the stack pointer. We restore the stack pointer value, and we perform a functional call. Return address is stored on the stack, and function use stack space for its local variables. As we can see, unbalanced stack canaries are not corrupted. Let's see what happens if we are calling function which is hooked by Cuckoo Monitor. We move through the same steps as previously. What we do next, we call a function, but now hook is executed, so it uses some space on the stack, and only after that it calls original function that also uses some space on the stack. As we can see, unbalanced stack canaries are corrupted, so Cuckoo Monitor is detected. One of the proposed solutions is, of course, usage of kernel mode hooking, but if you want to stay with user mode, the following tactics may be applied. We move through the same steps as previously. But what we do in our hook, we move stack pointer on the address that are lower than unbalanced stack canaries, and we copy function arguments. And only after that, we call our hooked function. As we can see, space used by hook and space used by function local variables does not affect unbalanced stack canaries at all. So let's talk a little bit now on the sleep skip logic implemented in Cuckoo Monitor. According to the first conditions, only delays within the first gsleep max skip second are skipped. The second feature is usage of global variable gtime skip that is used for accumulating of skip delays. And this is the second place where the problem exists. The third feature that actually implements skipping is implemented here. Real delay is replaced with a 0.1 millisecond. So let's take a look where sleep skip function and these global variables are used. Sleep skip function is used in anti-delay execution hook, and gtime skip global variable is used in system datetime related functions such as anti-query system time, get tcount, get local time, get system time as file time functions. Okay, let's move to handling of infinite delay by anti-delay execution function. When the application calls sleep with infinite delay, it moves down and calls sleepx function with infinite delay. However, sleep function converts infinite delay in appropriate manner and passes it to anti-delay execution as an argument. With such a delay interval, thread will sleep forever. Let's see what is wrong when the anti-delay execution is hooked by the Cuckoo Monitor. We have the same route till the anti-delay execution. But what happens now, the anti-delay execution cook calls sleep skip function, and delay interval is replaced with 0.1 millisecond. So anti-delay execution original function will be executed with delay interval that equals to 0.1 milliseconds. So instead of sleeping forever, thread will sleep only for 0.1 milliseconds, thus cuckoo is detected. Proposed solution for such a detection is just to add one additional condition that checks delay interval value. Let's take a look at the delays accumulation problem. When we are calling sleep family functions, the delay interval is added to the global variable gtime skipped. And when we call anti-query system time functions, Cuckoo monitor hook performs syscall for anti-query system time functions, and after that it adds a global variable gtime skipped value to the time it received. So basically it's done in order to avoid detection by skip delays. So, but what we can do, in the first thread we can query current system time, and after that we can start waiting for some object for 100 milliseconds, for example. In the second thread we call sleepx function with a delay interval that equals, for example, 3 days. Thus, this delay interval is added to gtime skipped global variable. After waiting for 100 milliseconds in the first thread, we simply call anti-query system time function for the second time, and we compare the difference between current system time and previously queried system time. And if it's more than like 1 day or a few days, we can tell that we have detected cuckoo, because after waiting for 100 milliseconds for some object, system time will change for about 3 days. Okay, so the first evasion technique we want to describe today is skipping of delays only within the first gsleep max skips millisecond from the analysis start. Let's take a look at the evasion technique. We perform some time-consuming operations within the first gsleep max skips milliseconds. And after that, we can perform many large delay skips, thus exceeding the critical timeout for the execution. After that, we can perform any malicious activities we want, because guest manager already sent a signal to the VM that it should be shut down. So the proposed solution is to skip all delays that are larger than some constant value, and for smaller delays, we can use sliding window technique. This technique is described on the current slide. We collect the number of hits for a delay within the last 10 seconds. And if the number of hits for some delay exceeds upper limit, then we skip the delay till the end of execution. As each technique, it has its own pluses and minuses. The pluses are that we skip all large delays, and small delays are limited set are skipped. However, the minus is that distribution of delays between 0 and gsleep mean skip delay may be pretty high. Thus, for specific delays, the upper limit will not be exceeded. To solve that problem, we can actually group delays into swarms. Let's take a brief look at the communication architecture between host and guest virtual machines. On the host virtual machine, guest manager is responsible for sending requests to the guest virtual machine. And in the guest virtual machine, we have a server that is called agent, and it's responsible for sending responses to the host machine. So agent is responsible for communication with host, as it was mentioned on the previous slide, and guest machine initialization and starting of modules that is responsible for malware tracking. The name of that module is analyzer, and we will discuss it later. So some implementation details that will help us to detect the presence of agent is it listens on all interfaces on 8000 port. Actually, detection may be performed on any port. And it uses simple XML RPC server class for communication interface. So to detect running agent, all we need to do is just simply enumerate all listening sockets, send crafted packet, and wait for response. If we received a specific response, then we assume that we are running in Cuckoo Sandbox environment. An example of crafted packet is presented on the left side, and example of response is presented on the right side. Our proposed solution is present on the current slide. If the connection request is coming from external interface, then we simply accept it. And if it comes from internal interface, then we reject it. Okay, as it was mentioned earlier, analyzer module is responsible for initialization of analysis procedure. Execution of analysis procedures that's handling pipe messages coming from Cuckoo monitor. So some implementation details. It is started by the agent module, and its location is calculated in the random way. So as we can see on the screen, the container is the name of the folder that is created under a system drive, and the name is generated randomly. But the problem is that in that folder we store two files with name analyzer.py and analysis.conf, and this looks like an easy way to detect presence of Cuckoo Sandbox. All we need to do, we enumerate on folders on system drive. We check if any folder contains both files, and if files are present, then we assume that we are running Cuckoo Sandbox environment. The proposed solution is pretty straightforward. What we should do, we generate a random name for the analyzer module, and we generate the random name for the configuration file and pass it as an argument to the analyzer module. Let's move to a very cool evasion technique that may be used by malware authors to avoid behavior monitoring by Cuckoo Sandbox. At the beginning, we have to take a look on how analyzer decides to inject or not to inject code into the process. If the analyzer process list already contains a PID we want to inject a monitor, we just perform some operations and return from the function without injecting code. However, if it does not contain the PID, we add this PID to the process list, and we start injection process. As the PIDs are added to the process list, they should be removed somewhere as well. The analyzer checks if the process is still alive, and if it's not, then it removes PID from the process list. However, this branch will be executed only when PID check equals true. But if we will force it to be false, then this branch will never be executed, so no PIDs will be deleted from the process list. We can easily force PID check to be false by specifying in first timeout argument to the cuckoo. So as on Windows system, PIDs can repeat quite often. We can create a list of already used PIDs, and we can, in the infinite loop, we can create a process and check if process belongs to our list. If it doesn't, then we add this PID to our list. At the same time, analyzer adds this PID to the process list. But when we meet a PID that is already in our PIDs list, that simply means that the process list already contains that PID as well, because it was not removed, even if it was killed. So monitor code will not be injected here, so Cuckoo Sandbox behavior analysis was avoided. The proposed solution is simple. When the monitor process calls exit process family functions, the kill command is sent via pipe. So we can handle it and add just one line that removes the PID from the process list. The next evasion technique we want to describe is related to a Windows feature. The name of that feature is Task Scheduler. It's used for scheduling tasks for a specific time or interval. It's available on all versions of Windows starting from Windows 95, and the main feature we will use is that task creation is not handled at all by Cuckoo Monitor. So we have a malicious process named process1, and we have task database. In the process, we create a new task named SE task. And after that, we start that process. And we can perform any malicious activity we want because process created as task objects are not monitored by Cuckoo. The last way to evade Cuckoo Sandbox that we found is very simple and cool. As we can see, we have DLL main function. It's the entry function of Cuckoo Monitor module injected to the process. Everything looks fine except of this check. If isIgnore process function returns something except of 0, then we basically skip monitor initialization functions. So let's check how we can force isIgnore process to return something except of 0. We should simply create process from one of the paths from the gignored process path list. So we check one file from the whitelisted process list. We create this process in suspended state. Now Cuckoo Monitor initialization routines were not executed. And what we do now, we simply inject malicious code and resume thread. So whitelisted process is not monitored. Okay, so proposed solution is just to remove all process paths from the whitelist. Let's move to the next detection technique that is based on number of occurred exceptions. As you can see, we have a static variable that is responsible for accumulating occurred exceptions, and we check if it equals to some hard-coded value. And if it's true, then we simply exit the process with error code 1. Let's see where log exception is used. It's used in a RTL dispatch exception hook. So if occurred exception is not whitelisted, then this function is called. So to detect presence of Cuckoo Sandbox environment, we create a second process. In the second process, we simply erase exception max count plus 1 exceptions, and if RTL dispatch exception is hooked, then the process will exit with error code 1. If it's not hooked, then it will exit with error code 0. So in the first process, we just collect process exit code, and if it equals 1, then it means that Cuckoo Sandbox was detected. The last detection technique for Cuckoo Sandbox we want to present today is based on configuration file that is responsible for configuration of Cuckoo monitor in tracked process. The problem is that location of that file is well known, and it's located under C drive, and file name is cuckoo.d.ini. So we simply create some process in suspended state. As far as we have process ID, we check the C drive for the presence of cuckoo.d.ini file for a few times with some delay. If such a file is present, then assume that we are running inside Cuckoo Sandbox environment. Okay, that's all for Cuckoo Sandbox. Now I will pass presentation to Alex, and he will tell you about virtual environment detection techniques and sandbox tool we have created.
Okay, thanks, Stanislav. So now let's talk about the techniques which may be used to detect your virtual environment itself. So the first technique is based on the fact that tampering with a date and time in your virtualized environments. So the detection based on 3 main points. In real environment, the system time should correlate with the web time. We should not see a lot of difference here for obvious reasons. So another thing, as we want to execute as much code as possible in a very limited amount of time of the emulation, we need to utilize the sleep skipping functionality. And the third one, that sometimes in virtual environments, responses from the web services are emulated, because you most probably don't want to use the dirty line connection option in Cuckoo. So let's see how all these can lead us to the detection. We have a process number 1, which performs the following operations. First of all, it gets local time, and then it gets the web time, for example, by sending a request to Google servers and parsing the response. In the next step, it sleeps for 60 seconds, and then it repeats the same operations once again. It sends a response to the remote server and sends a request and gets a response. So we can assume that if the difference between the web time and the local time is more than 5 seconds, then most likely we're running in the virtualized environment. It can be either emulation of web services or sleep skipping technique. Also, we can tell more specifically what happened here by executing 2 additional checks. If we observe that the time delta between the first and second function calls are less than 60 seconds that we've tried to sleep initially, most likely something is emulated, either web services or sleep. So the second technique is based on the fact that usually sandbox VMs only run on a single core, while real machines utilize more than one, of course. So malware uses a fact and checks the number of processors and by solve figures whether it's running in the virtualized environment or not. Let's take a look at how the number of cores can be retrieved nowadays by the malware in the wild. First of all, it can use the function gets system info. It can get it directly from PAB, or it can use get native system info API. Unfortunately, all these can be patched, We've discovered a new technique which we haven't seen in the wild yet, but most likely we would if the bad guys are watching us. So here it is. First, we get a number of potential cores by one of the standard methods mentioned on the previous slide. As each core represents a logical processor, we can set a thread affinity mask in the way that will allow our thread to run only on that specific core. Then we run CPU on the instruction, and as a result, we get an API CID for that specific logical core and put it in the unique set. We repeat this step for each core. Finally, if this unique set size is less the number of detected cores, then we know that most likely we are dealing with the hooked function, which tampers with the number of cores, resulting in virtual environment detection. By the way, there is no fix for that yet. So another well-known technique is detection by raw firmware table content. This technique was first implemented in VMD tool, and on the Pre-Vista systems, the content can be retrieved by using the anti-read virtual memory syscall from the CSRSS service. And on the Vista and above systems, content of those tables can be retrieved by using anti-query system information function. The fact is that even this technique is well known, there is no proposed solution for that yet. So we've prepared one for you. As there are two different implementations, the solutions will also differ. So on the Pre-Vista systems, we propose using anti-read virtual memory service splicing. You should check if the read address is equal to C for zeros or E for zeros. If it is, then you should modify the buffer, which will return to the user space by either removing the artifacts or just returning another legitimate buffer here. On the Vista and higher systems, we propose hooking the anti-query system information service. First, you should check if the system information class is equal to system firmware table information. Then we parse system firmware table information structure and get provider signature and table ID fields. Then we check if the provider signature is either firm or RSMB. And then we are calling an original anti-query information routine and taking the same measures as we do with the Pre-Vista systems, modifying the buffer that will be returned to the user space. So since we discovered a lot of new detection techniques for Cuckoo Sandbox, as well as virtual environments, and proposed fixes for that, we realized that at the moment there is no such tool on the internet that will allow you to assess your virtual environments in an easy and reliable way, and will contain the most recent and up-to-date detection techniques. Also, existing tools will only tell you what they found, but know how to fix it. So we decided to create our own tool that will address all these drawbacks. More than that, anyone can contribute to that tool, even without touching the source code at all. So as I already mentioned, we wanted a generic tool that will cover a lot of different virtual environments, detection techniques, and we'll propose fixes for that. We wanted it to be easily extendable, so the support for new virtual environments can be added quickly. Also, since Cuckoo Sandbox is the most prevalent tool for automated malware analysis, we wanted to include the detection of it as well. In addition, we wanted to create an ability to introduce new detection techniques not through modifying the source code, but by using the JSON configuration files, so the whole community can contribute towards the development of that tool. And finally, we wanted user-friendly reports about the checked environment, and that can be shared within the organization among purely technical guys and also higher management. So we support three specific environments such as Cuckoo Sandbox, VirtualBox, VMware, and also a set of generic detections that can be assigned to any specific environment. Generic detections may be based on registry keys, devices, files, processes, MAC addresses, network adapters, disk names, firmware contents, system object contents, processor vendors, Windows names, and shell folders, etc. So for example, let's take a look at the configuration file content, specifically the part that utilizes registry key detection. As you may notice, we can specify more than one artifact, so that the search will be performed on the set of artifacts, which is quite useful. And we can also add the key recursive that will allow us to enumerate all the subkeys within the parent key. Also, configuration supports all previously mentioned artifacts as well. So to add a new detection artifact, we just need to add a new entry in the configuration file. There is absolutely no need to do recompilation of the two. As an example, we can add such a section in the configuration file to detect virtual environments based on a specific device. So if we want to add a new virtual environment support, we just need to implement the following template. So it's pretty easy. Let's move on to the output interfaces. Here is a list of output options that we have. We can output the report. This is the most user-friendly version of the output. You'll get like a nice HTML file with a description of detection techniques and also with advices on how to fix them. The second option is output to the console. This method is usually used for to get the debug information. And the third one is we can generate a file for each specific detection technique, and the file name will contain detection technique name plus detected or not detected postfix. And this method is most convenient for checking the environments where you don't have a full access, and you can just upload the file, such as VirusTotal or Malwr or any other sandbox out there. So here is a sample of the report, how the report looks like. It's just like a part of it. It's usually much bigger, but it looks like that. So let's sum up. We've presented a lot of new detection innovations for Cuckoo Sandbox today, and we hope that they will be fixed as soon as possible by either Cuckoo authors or by the community. We're in contact with the Cuckoo developers, and we're willing to help and share information. We've developed an easily extendable tool for virtual environments assessments, which supports easy interface for adding new environments, addition of new detection techniques using configuration files, and also multiple output options. The most important part is that our tool is available as open source. So now it's time for questions. Thank you.
Thank you. Thank you for your interesting talk. And there are any questions here? Right there.
Have you seen malware authors adapt their techniques based on the work that you've done so far?
Basically, I think that we've presented a lot of new techniques, so I think that malware authors will adapt them. But as I said, we're within the contact with the Cuckoo authors, so we hope that those bugs will be fixed before anybody can do any harm. So we're willing to share information, so if you have any requests, please contact us, and we'll provide technical information, so no problem.
Other questions here?
Hi, so how the Cuckoo Evasion techniques works on the Spender's fork?
Sorry, on what?
So how they are working, if they are the same working in the Spender's fork, or because you are testing them on the upstream mainline side, the guys from the Cuckoo Foundation. Did you test the same techniques on the other fork?
What do you mean by other fork? We have tested it on RC1, like the latest, stable version.
Okay.
So
yeah. You didn't test the Cuckoo modified fork?
No, we haven't.
Okay, thanks.
I'm afraid we are running out of time, so if you have any further questions, you can contact directly the speakers. So thank you very much.
Thanks.